Okay, so today we are going to be getting into combustion efficiency testing. Now, before you watch and listen to this presentation, it is advised that you go back and listen to the presentation on combustion, because these two presentations kind of go hand in hand with the whole combustion process. This presentation is definitely going to be covering how we come about achieving efficiency in oil heat type of appliances. So, combustion efficiency testing is one of the most important things we do as a service technician dealing with oil. We have to make sure it's our job to make sure that we are doing these tests. As an oil technician, we should be doing these tests on maintenances of these equipment and at service calls on these types of equipment. They should be done pretty much anytime we touch them. You should do an efficiency test. You should do an efficiency test before you make any sort of adjustments and repairs to that unit, and then you should do another efficiency test after you have made any adjustments and repairs. Okay? Combustion efficiency tests is the only way as a service mechanic can tell us whether or not an oil burner is operating at its highest and safest efficiency. We have to make sure that these things are doing what they're supposed to do. Okay, it is imperative to perform a combustion analysis during routine service or any time changes are made that will affect the combustion of that unit. Combustion testing provides numerous benefits to the customer and the technician. Obviously, it's going to save money for the customer. It's going to save time on any sort of nuisance service calls and repairs. You're going to avoid a lot of callbacks simply due to the fact that if a furnace is set up correctly and operating the way it's supposed to, it's very unlikely that it's going to have any real catastrophic problems in the long run. It's limiting your liability. It's maintaining equipment warranty. You're providing confidence to the homeowner that the unit is going to operate efficiently without very little problems. It's going to provide increased comfort simply due to the fact is that it's running efficiently and it's not going to soot up every other day. Providing increased safety increases energy efficiency and obviously lowers environmental emissions. The most important setting you make on an oil burner is excess air. You cannot really do this without any sort of instruments or any sort of test equipment. So again, the principles of combustion is combustion test instruments measure the composition and temperature of flue gases as they leave the boiler or furnace. Okay, you can also measure the amount of smoke and draft produced in order to properly adjust the flame and identify problems. Right there is really important when we are thinking about combustion efficiency. We are measuring things. We are measuring temperatures of the flue gases. We are measuring the amount of smoke that's going out the flue pipe. We are measuring the draft in our flues to see whether or not we have problems. Okay, combustion testing measurements is definitely temperatures of the flue gases, draft produced by the chimney, whether that's power vented or just a simple standard venting system. You are going to measure your smoke concentrations in the flue gases. You are going to measure the composition of the flue gases, how much excess air you have, how much CO2, how much O2, and how much NOx emissions you are going to be emitting. You are also measuring carbon monoxide concentrations in the flue gases. Okay, the three things we adjust that affect the combustion processes are fuel pressure. Remember, standard oil burners are pretty much operated at 100 psi. Newer burners are operating at approximately maybe 130, 150 psi. Okay, we are going to be adjusting combustion air. We are also going to be adjusting draft through our units. Other factors that affect combustion process is obviously flame impingement, which is something we do not want because flame impingement can cause carbon monoxide. Okay, excess air leakage into the heat exchanger. Okay, we want to make sure that we have insufficient air due to tight construction or improper ventilation. So we want to make sure that we are have enough air for that unit to run correctly, and if not, we are going to have to make provisions to make it so. Okay, improperly installed vent systems obviously has always been is usually not usually a problem, but it depends on who puts it in. If Johnny homeowner likes to put stuff in by himself, chances are they probably screwed up the venting system. One thing when it comes to venting is that you want to try to keep it as straight as possible with as little turns as possible. Okay, combustion testing equipment. You are going to have two separate types that are out there. Okay, you have your manual equipment, which is like the old back rack kit right here that you see here on the left. This blue case has all these nice little test equipments in there. Or then you have your digital electronic test measurements, which does everything at live action. I have both in my disposal. It depends on how I want to do things. Sometimes I like to take them both just to compare, you know, apples to oranges and see how things are. The problem is with the older types of equipment, it's time consuming. Okay, it only gives you a fuzzy snapshot of how the burner is performing. Anytime you make an adjustment with the older style like back rack kits, you have to redo the test over again. So anytime you adjust like an air band on the oil burner, you have to go back and measure your stack temperature and measure your O2 and your carbon monoxide and all that stuff over again. With the digital one, it's all live action. Anytime you make an adjustment on an oil burner, the screen it just shows you what's going on. It shows you the readings like automatically. Okay, when we're taking our measurements, we want to be taking measurements through a 3/8 inch hole drilled in the flue pipe near the boiler or the furnace outlet. Okay, that hole has to be at least 6 inches from the draft regulator on the furnace or boiler side of the regulator. You have to make sure that you are taking these measurements in the correct area. If not, you are going to have false readings. You're going to get something that's wrong. Okay, you also need a hole in the fire or observation door over the burner. Okay, some new units do not have a door for over the fire. When we are taking our draft readings, we are going to be taking our draft readings in those two areas. We're going to be taking them in our flue pipe, our breech, as we like to call it, and over the fire. We need to make sure that we are taking those readings. Okay, to successfully adjust your burners with the manual equipment, you are going to need, obviously, to test for draft. Okay, so you're going to need a draft gauge. Your draft gauge is right here, this big black box. Okay, you're going to test for smoke. Okay, so you're going to need a smoke tester and a smoke scale. That's what this guy is right here. Okay, this is our smoke tester and our smoke gauge. Okay, you're going to need our carbon dioxide tester, or better known as an ORStat tester, which is this guy right here. Okay? This guy and our pump all go together. Okay, the stack thermometer, which is used to measure the temperature of the flue gases, is right here. That stack thermometer is going to range from 200 to 1,000 degrees. Okay, we need a combustion efficiency slide rule to calculate the efficiency, which is right down here. So all of these components are what is for your manual testing equipment. You are going to have to take each one of these tests and do them individually. While not needed to calculate efficiency, it is important to know if the oil pressure to the nozzle is correct. And measure this, we need a pressure gauge capable of reading up to at least 300 psi or 300 pounds of pressure. Here is a great tool to have. This is actually a dual pressure pump pressure manifold gauge set from Metco. I have this exact pump pressure test gauge. It measures my pump pressure, and it also can measure my vacuum as well. The clear tubes is my vacuum. The red and yellow would be for my pressure. Okay, I can literally take a reading on both at the exact same time. So, step-by-step procedures when you are taking a traditional type of efficiency test. The first thing that you got to do is you're going to take the stack temperature. Okay, so with the manual equipment, 2 holes will speed up the testing, and the thermometer should be placed into the unit on start, and the rest of the test done in the other hole when the temperature reading actually stabilizes. The next step you're going to do is you're going to take a draft reading. Okay, you're going to do the draft second because the other test will be affected by any increase or decrease of draft. Okay, then you're going to take a smoke test. Okay, you're going to adjust for 0 smoke on the burner. Okay, you start by opening the burner air shutter or adjusting the head. Then you're going to then fine-tune the air to reach 0 smoke. Okay, rule of thumb is 0 to 1 when you are doing these types of tests. Next, you are going to take a CO2 or an O2 reading. Okay, this is done last because if draft or smoke is wrong, it's going to affect your CO2 reading. Okay, and you cannot leave a unit this way. You have to make sure that you have the correct and your smoke readings where they're supposed to be. Then, after all that is done, then you are going to calculate the efficiency using the slide rule. Okay, once the air is adjusted properly, you're going to take a final temperature reading and compare the CO2 reading to the net stack temperature using the slide rule to get the combustion efficiency of the unit. Okay, to get a net stack temperature reading, you are going to measure the flue pipe temperature using the thermometer. Then you are going to subtract that temperature reading from the room temperature. So say, for example, if you are reading a net or reading a stack temperature of 400 degrees and you are in a room that is at 50 degrees, 400 minus 50 is 350. That is your net stack temperature. You are going to base your readings off of that reading, off of that temperature. Okay? Make a record of the results of each test on a combustion survey. Write them down, whatever it is that you're getting. Okay? Which will show all before and after readings. Then you will know how much improvement you have actually achieved, or if you've done it actually wrong and actually gone down in efficiency, which is something you do not want. Okay? When we do these tests, we want to make sure that these furnaces achieve what is called a steady state. Okay? Those are your best accurate test results. Okay? And that's when those measurements should be made. Steady state is the point at which your stack temperature stops rising, and that is going to usually occur after about 5 to 10 minutes of runtime. Okay? So anytime we are doing an efficiency test on an oil furnace, we have to let them run. Let them get up to temperature. Let your flue pipe get up to temperature before you start taking any readings. Your stack temperature, or flue gas temperature, is the temperature of the combustion gases leaving the appliance and reflects the energy that did not transfer from the fuel to the heat exchanger. The lower the stack temperature, the more effective the heat exchanger design in heat transfer. Stack temperature is a measurement of the heat exchanger's ability to draw the heat from the combustion gases. That's why we take these readings. So as the excess air goes up, so does your stack temperature. Okay, so understand why this actually happens. We have to look at the heat exchanger. The longer the combustion gases are in a heat exchanger, the more the heat the exchanger can pull from it. Okay, and when it's the more it can pull from it, the lower the stack temperature is going to be. So as the excess air increases, so does the volume of your combustion gases, as you can kind of see on this chart here. Okay, the lower my stack temperature, the more volume I have, or the less volume I have. Okay, so it's really important to make sure that we have, again, back to combustion, we got to have the correct air-fuel mixture. Okay, the volume of gases traveling through a heat exchanger determines how fast the gases must travel. The more air we put in, the faster it goes. The less time the heat exchanger has to suck the heat out from the gases. As the excess air goes up, the stack temperature does too, even though the flame temperature is reduced. As stack temperature goes up, efficiency is going to go down. Okay, and our customer is actually losing money when this happens. So when we are doing an efficiency test, we want to try and keep our stack temperature within the correct ranges. Okay, the primary importance of your stack temperature is to provide enough heat in the flue to prevent water formation. Remember, we don't want that to happen. If we have water formation inside our flue pipe, it's going to corrode the flue pipe. Okay, the flue gas temperatures and all other tests should be measured in the flue gas hot spot. This is the point in the center of the flue where the stack temperature and the CO2 are at their highest level. Okay, and the O2 is at its lowest. Condensing in non-condensing appliances can cause your chimney to deteriorate, it can cause your chimney liner to fail, and it's going to cause rust inside the appliance. Taking a gross stack temperature reading, you're going to subtract the temperature of the air entering the burner, which is your ambient temperature, from the gross stack temperature to get the net stack temperature needed to calculate your efficiency. Again, that is really, really important when you are doing these readings. Take the flue gas temperature using the thermometer. Again, notice how I am repeating this. You take the thermometer, measure your flue gas temperature, and subtract the room temperature from that reading to get a net stack temperature. The relationship between the percentage of excess air in the flue gases, which is your CO2 or O2, and the net stack temperature is going to give you your combustion efficiency. Okay, what's going to cause high stack temperature? Well, the first culprit is going to be soot. Okay? Soot is an insulator. It's going to affect how good heat of a heat transfer that oil is going to be able to give to the heat exchanger. In fact, inspecting the heat exchanger, clean it if necessary, and adjust the burner to 0 to trace smoke. That is the best way to eliminate your soot deposits. You do not want smoke. Okay? Excess air. Remember, excess air cools the combustion gases and increases their volume. This results in lower heat exchanger efficiency. Excess air can be due to poor air-fuel mixing. Again, back to that. Your poor burner adjustments, okay, which means you have your air collars aren't set up. You have maybe too much or too little air going in there. Okay, more air is needed to stop smoke. Okay, and leaks into the heat exchanger. You have to make sure that your burner is sealed. Your gaskets are in place. There are no areas of air that can come into that burner other than where we want the air to come into that burner, which is through our air collars. Overfiring a furnace is going to cause high stack temperatures. Okay? Firing the heating system at a higher GPH than it was designed for causes high rates of gas flow through the heat exchanger and results in high stack temperature. Okay? To prevent condensation, your stack temperature should be anywhere between 270 and 370 degrees above the ambient temperature for non-condensing appliances, which is typically all of your oil-fired equipment. That's a key. Those are key temperatures right there. 270 to about 370 degrees. That's where you want your temperatures to be. Okay? Draft. Okay, is the flow of air and combustion gases through the burner, heating unit, and your venting system. Draft is required to remove the flue gases from the heat exchanger during steady state, which is, remember, after about 5-10 minutes of operation. Okay, the draft should be stable. Your over-the-fire draft should be negative 0.01 to negative 0.02 inches of water column. That's generally what we recommend on your residential units. Common causes for poor draft is problem with the chimney. Chimney is too small for the load of the attached appliance. The chimney is too large in diameter or cross-section. Chimney is too short or improperly constructed. Leakage of air into the chimney, thimble, stack, or breaching. Obstruction in the chimney at the top or at the top of the chimney. The top of the chimney is lower than the peak of the house. Okay, your flue pipe diameter is too small, which, oh, by the way, it should never be any smaller than the breach size on the furnace itself. Okay, or you have too many elbows in there. Okay, you want to try to keep your flue pipes as straight as possible with as little turns as possible. Okay, keeping your smoke to a minimum is a must if the heating system is to operate at peak efficiency without further attention during the heating season. Okay, we measure smoke concentrations by taking a sample of the flue gases with a smoke tester and a smoke scale, which identifies your smoke by number from anywhere from 0 to 9. Okay, 0 is no smoke, 9 is heavy smoke. And as looking at the picture here, this is really what the smoke chart actually looks like. So when you take a smoke test, you compare your reading to each one of your number designations. If you see black smoke coming out like that, that's obviously a 9. That's no good. Okay? Any smoke number above a number 2 causes rapid soot accumulation on your heat exchanger surfaces, which is why when we take our smoke readings, we want 0 to 1. That's it. Nothing more than that. If you have more than that, you need to make adjustments to that burner before you do anything else. To reach high efficiency, you must adjust your burners for 0 smoke and the low excess air while maintaining a high level of CO2, okay, or a low level of O2. Okay, a typical smoke tester draws a total of about 2,200 cubic centimeters of flue products through a standard grade filter paper, okay, and that's usually when we take it and we do 10 full strokes of our smoke test using our pump to get that amount of sample. An oily or yellow smoke spot on your filter paper is a sign of unburned fuel, indicating obviously poor combustion. Causes of smoke and all that other stuff is poor fuel atomization. The fuel droplets are vaporized quicker than your larger ones. Your larger droplets are going to be caused by damaged or worn nozzle, which obviously anytime we're doing a service or a maintenance on there, we are changing the nozzle no matter what. You're going to have low fuel pump pressure, which is, again, is why it's always important to take fuel pressures to see what you're actually pumping at. Or you have cold oil. Okay, remember, cold oil, viscosity. All that stuff takes into effect as to why you're having smoke. Sometimes as the oil heats up, the smoke goes away. Okay, inadequate combustion air is caused by the burner air control is not open far enough. You have poor chimney draft, built up soot and scale inside the heat exchanger, accumulation of lint, hair, sawdust, dirt inside the air shutters or on the burner fan, or restrictions of the airflow to the room the burner is in, and the operation of exhaust fans that depressurize the building are all problems that we have to look into when we have problems with our combustion. Okay, one thing that is nice to always have, if you can have at disposal, is some furnaces come with a troubleshooting chart, such as like you see here, that can kind of help you evaluate and come up with a remedy to fixing problems with a furnace that is actually not operating at its peak efficiency. For example, if you have a problem with a unit that's running with a high O2 reading, you can have problems with, obviously combustion air problems. The burner is under firing, so maybe you might want to look at your pump pressure or the size of the nozzle that is in the furnace. You might have loose clean-out ports, access door that might be not secured correctly, or a missing gasket or something like that that is on the burner that could be causing these issues. So you're going to want to adjust the air band. You're going to want to adjust the fuel input maybe, or obviously repair the gasket or whatever door might be missing or something like that. If you have low temperature rise or a furnace like that, or a low stack draft less than negative 0.02 in the flue, or negative 0.04 in the flue, okay, you're going to want to check maybe for blocked venting system. Maybe you have too many elbows, or the flue pipe has just ran too long. Okay, you're going to want to look into all of those things. So when we're thinking about draft, when we have our over the fire draft, we're looking at anywhere between negative 0.01 and negative 0.02 over the fire. If we are taking our breach or our flue draft, we're looking at anywhere between negative 0.03 and negative 0.04. Those are our rule of thumbs when we're looking at stuff like this. You have to make sure that you have the correct draft. If you have high draft or a high stack draft, say, for example, greater than 0.6, you're going to have to look at the venting on it. You're going to have to look at the barometric damper. Is the barometric damper set correctly? Okay? We need to set our barometric damper to what we're reading on our draft gauge. Is our draft gauge just not, is our barometric damper just flopping in the breeze? We have to make sure that all those things are correct. When installing new equipment or troubleshooting problem equipment, the first determination that needs to be made is whether the equipment is located in a confined or unconfined space. In accordance with NFPA 31 and NFPA 54, a confined space is defined as follows. Any space whose volume is equal to or greater than 50 cubic feet per 1,000 BTUs, or 20 BTUs per cubic foot. and this is calculated by the sum of the total input rating of all fuel burning appliances installed in that space. Only areas connected to the space that have no doors or with fully louvered doors can be considered part of the unconfined space. So how do we calculate whether or not we're in a confined space or not? So we have to take some measurements when we do so. Okay, so for example, we have a room that is 20 by 30 with an 8-foot ceiling. Okay, and the heating appliance is 140,000 BTUs. Okay, we have to determine the maximum total input firing rate allowable in the room without modifications. So we do some simple math. 20 by 30 by 8, that comes up with 4,800 cubic feet. Okay, we take that 4,800 cubic feet and we times it by 1,000 BTUs. Okay, or 50 cubic feet. All right, because that's what is in the definition of our unconfined space, right? 50 cubic feet per 1,000 BTUs, correct? All right, so we come up with that, and we come up with 96,000 BTUs. So now we know how much BTUs we can put into that one space. We take 96,000 BTUs and we times it by 1 gallon of number 2 fuel oil, right? And we divide it by 140,000 BTUs, which means we should have a nozzle of 0.69 gallons per hour inside there. That's the highest gallons per hour that we can use for that particular type of unit. So if we're firing above 0.69 gallons per hour or 96,000 BTUs, you have to make provisions for additional combustion air. We have to add air to that room. So there's 2 ways we can do that. So if we're going to add air from an adjacent room of this confined space, you have to have 2 openings between the room, and they could be made 12 inches above the floor and 12 inches below the ceiling. Okay, the size of these openings is based on 1 square inch per 1,000 BTU input. Okay, you can also do it in a different way. You can add air directly from outside of the structure, and if you're going to do it that way, you got to have 2 openings that have to be made. Okay, and those sizes of these openings is again based on 1 square inch per 4,000 BTUs of input. Okay, those above requirements are based on the guidelines again from NFPA 31 and NFPA 54. Okay, alternately, if operating in a confined space, additional air may be added by a duct or to the outside, again sized on 1 square inch per 5,000 BTUs of input.